Welcome to the morning session. We just have one talk today by Masataka Watanabe from Nagoya University, who's going to tell us about the physics of the split property.
Very nice, thank you. I'm going to talk about physics of the split property. I'm from Nagoya University. The date and place is wrong, but I promise that this is the only place where it's wrong, where the slides are wrong. Where is my clicker? Thank you. Right. No, it shouldn't be there. I don't. Sorry. All right. So today's goal is to define entanglement entropy, which you know very well, and obviously the reduced density matrix in CFTs. And there's a physics way that you know very well, which is to have a regularization, like H is equal to HA tensor HP, and you impose some suitable regularization. You know that very well. There is another way, which is the mathematics way, which is the split property of the phenomenal algebra. So what they say is that we can always approximate the algebra of operators, which is type 3, using a matrix algebra, which is type 1. And I will try to bridge these understandings. Right, so what is entanglement entropy in physics? It's very easy. So entanglement entropy in spin systems is very easy. The total state lives in H, the total Hilbert space, which is like, when you have two n qubits, n qubits, the total Hilbert space is isomorphic to C to 2n. And the density matrix is defined as rho, ket bra, all right? Right, so do ask me questions in the middle, because I'm not like the best speaker in the world, and there might be some confusing things I say. Do ask me questions. Right, the total Hilbert space is like C to the 2n, and the density matrix is just usually ket bra. And because it's a spin system, the Hilbert space tensor factorized. It's like HA tensor HA bar. By A, I mean that it's the green dots, which is a subregion, my subregion, and A bar, which is the outside of my subregion. And the reduced density matrix is obviously partial trace of rho, as usual. And you can define the Rayleigh entropy as 1 over 1 minus n times log of trace A to the rho A to the n. Trace A to rho n is usually 1, but in this case 1, but I added for clarification, for normalization, all right? So what's important is that rho A has discrete spectrum with integer multiplications, multiplicities. So it's easy to define what the trace A of rho A to the n, and take the log whatever you want. So the procedure is all finite. Doesn't move anymore. All right. Right, so next slides. The total state, entanglement entropy in 2D CFTs, I'm going to talk about it. The total state lives in usually as Hilbert space, which is countably infinitely dimensional, means it's separable. I'm trying to identify the two ends at x is equal to plus infinity and minus infinity, because I want my spectrum, my Hamiltonian has discrete spectrum, but doesn't really matter. Now I want to take the subsystem A to be minus L over 2 to L over 2, which is the interval. So if the Hilbert space tensor factorizes like HA tensor HA bar, you would have like rewritten psi as like sum of eigenstates of some factorized state, and then you can define the partial trace and define entanglement entropy. But we say there is no such thing. Why? It doesn't work. All right. So we can still compute the entanglement entropy in 2D CFTs, right? We do this with a regulator. So what does this mean? What does this mean to compute something with a regulator? So for example, what we usually do is the following. If you want to compute the reduced density matrix for the vacuum state, you do a path integral. So it's an unnormalized vacuum state. You start from any state, and you do a path integral. Imagine Euclidean time path integral, infinitely long, and you usually hit the vacuum state. That's how you create the vacuum state. But this is unnormalized. Now, the Kip-Browse vacuum state, which is a density matrix, is like, you leave these, you do this path integral from the lower half plane and upper half plane and leave these two boundary conditions free, okay? Now, if you want to compute the trace, partial trace, taken on A bar, you just glue these two regions, written in purple, and leave these green regions as free boundary conditions, okay? So that's my partial trait, reduced density matrix. However, the state is not normalized. For example, if you want to compute the overlap between vacuum, it's like the sphere partition function in 2D. So it's divergent, and you need to regularize it to define it. So for example, it's like log of epsilon or lambda. Lambda is like 1 over epsilon. Okay, any questions? Okay. So now you do the replica trick because you want to compute, compute row A to the n, right? So in computing the row A to the n, you, as usual, you do the matrix multiplication of the reduced density matrices, and you take the trace. So you have purple region identified with the purple region in sheet 2, orange region in sheet 2, identified with orange region in sheet 3, and so on and so forth. I'm showing the graph. I'm showing the figure for n equals to 3, but you can easily generalize it to arbitrary Renyi index. Anyhow, so people say the following. So people say that this can be computed as a 2-point function of the twist operator, which I call by sigma n, inserted on 2 entanglement points, right? So it's a trace row A to the n is proportional to the 2-point function of the twist operators, all right? Any questions? Yes, thank you. Right. I guess there are no questions because it's still very elementary, but it's very important that this is a proportional instead of equal sign, which I will going to explain. Thank you very much. So now that it's exponential of the nth Renyi entropy, this is traced row A to the n. This is proportional to the 2-point function of the twist operators. So because the twist operator has dimension c over 12 times n plus 1 over n, I'm sorry, it's n plus 1 over n. It's proportional to L. L is the length of the subsystem, and you take the power minus c over 12 times n plus 1 over n, right? So this is weird, right? I mean, the left-hand side is dimensionless, while the right-hand side is dimension full, okay? The overall normalization of the scale, this is okay because of dimensional transmutation. When you want to compute sphere partition function or any partition function, you need to introduce a scale because you're in 2D CFT, a continuum theory. Now, what you do is to fix it by introducing the UV regulator with scale epsilon. So people define the entanglement entropy to be people take out the portion of the entanglement entropy, which is L over epsilon to some power. Some like minus c over 12 times n plus n, 1 over n. Okay. So you need to regularize the theory to define entanglement entropy in QFT. All right? Any questions? All right. But does this really make sense? I don't think it makes sense. Quantum information theory wants to reduce density matrix to discrete spectrum with integer multiplications after regulating it, because otherwise you don't know what it is. So this means after diagonalization of the reduced density matrix, you need to have, you diagonalize it, row A is a diagonal matrix whose eigenvalues are A0 to AN, to A infinity. So if you take out the largest eigenvalue of row N, I will write it because maybe it's confusing. So row A is proportional to, A1, A0, A1 dot, dot, dot. And A0 is the largest eigenvalue. So obviously, if you expand it to large N, you have A0 to the N, and 1 plus A1 over A0 to the N, and so on and so forth. You should have that in order to interpret that in terms of quantum information theory. But if you expand your result for the twist operator formalism at large N, you will find 1 over N piece. This is not consistent with the above, So this means that your regularized reduced density matrix still has continuous spectrum, and it doesn't have integer multiplicities. Oh, because you can integrate integrate your eigenvalues. Oh, the question was if why it's continuous spectrum. The answer is that because you can make the above sum into an integral, and you can make any 1/n scaling, and that's what it is. You can do a Laplace transform of this one to recover the would-be density of states, and that's fine. But it's continuous.
So sorry, but I would have just thought that, okay, you take that second term over there, identify it with A1 over A0 to the power n.
What again?
I would have thought that the story is that you take the second term over there, identify it with A1 over A0 to the power of n.
You can't do that because it's a power of n, it's a 1 over n, and we're at large n. But you can still do a Laplace transform to take out the density of states for the reduced density matrix.
Okay, thanks.
Now, so rho A is defined right now, has continuous spectrum again, and even after regularization, this is not consistent with probabilistic interpretation of entanglement entropy. Yes?
If the spectrum is discrete, so is this expansion computed using some average smoothing out like you do in the Cardi formula case? Or?
Smoothing out, what do you mean?
The spectrum is discrete, right?
Yes. Oh, I understand. But because we're looking at the lower end of the spectrum, you don't have this problem. I guess you're talking about, when you usually compute the Cardi formula, because you take large C or large dimensions, it looks continuous instead of, I'm not looking at that region.
Oh, I'm sorry.
Right, because n is the replica number. It's like the inverse temperature. So you're looking at the low temperature region.
Actually, related to his question, I think one of the ways to get the usual formula for any entropy in CFT is that you basically put little holes around the endpoints and then conformally map the manifold to a cylinder. Okay, and then the Renyi entropy is really thermodynamic entropy in the open, in the interval channel.
I will get to that.
Then over there is a manifestly discrete spectrum, right?
I will get to this. Very nice. So it seems like one cannot take arbitrary regularizations to define entanglement entropy, right? Because when you try to do that with naive twist operator prescription, you don't get consistent result. So what are the actual correct regularization to define entanglement entropy? And will they affect the physics, even though they're just UV cutoffs? Right, any questions? Even though, right, probably not. Very nice. So let us compute the entanglement entropy again in a different way, which makes it manifest what the regulator is. So we needed to compute the partition function with the nth branch cut in a Z frame. Z frame is the left frame. So you have branch cut lying in the purple region. You have two twist operators. So I would say two entanglement points at -L/2 and L/2, and there is a branch cut connecting them. Okay. And then if you go n times around the entanglement points, you go back to itself, all right? So you do a conformal transformation. W is equal to log of Z plus L/2 over Z minus L/2, whatever. So this has the effect of mapping for example, the imaginary Z axis to the middle of the cylinder, red circles to red circles and so on. It maps a plane to a cylinder. And because of the branch cut, the circumference of the circle is 2 pi n instead of 2 pi, and the length of the cylinder is infinite. So the geometry now is an infinitely long cylinder, and it is now clear why entanglement entropy is divergent without a cutoff. There is an IR divergence in the W plane, the right plane, with a continuous entanglement spectrum. Right. So there are roughly two ways to regulate it, right? By chopping the two ends off with boundary conditions. So you have very long cylinder, you can chop them off at finite length, or you can impose a periodic boundary condition. So after conformal transformations, you reach a finite length cylinder or torus, finite size torus. And this is equivalent to having UV cutoff in the Z plane, the left plane, because this the blue region maps to the blue circles around the entangling points, and that's if you call the circumference of the circumference of the UV cutoff to be epsilon, the length of the finite size cylinder is 2 times log L over epsilon. Okay. Right. So if you view it in the left frame, it's a UV cutoff, while if you look at it in the right frame, it's an IR cutoff. Right, any questions? Okay. So it is clear that this cutoff is compatible with quantum information theory, probabilistic interpretations. Because, for example, if you look at this left figure, it's a finite-sized cylinder, and if you want to compute the partition function of the cylinder, you compute the thermal trace of the modular Hamiltonian or the interval Hamiltonian, right, with the temperature 2 pi n and length 2 times log L over epsilon. And if you were to impose a periodic boundary condition, you would do the same thing, roughly the same thing. Right, so in other words, the regularized modular Hamiltonian is a Hamiltonian on an interval or a circle. And this is discrete spectra right, for non-pathological CFTs and non-pathological boundary conditions. So after all, the reduced density matrix depends on the way you regularize. It's not just a simple epsilon dependence that you see in textbooks.
But I think there's a paper by Lingyan Hung and Gabriel Wong where they show that you get exactly the twist operator formula with an appropriate sum over Cardi boundary conditions.
What?
It's a paper by Lingyan Hung and Gabriel Wong.
Who?
Lingyan Hung and Gabriel Wong.
That paper, right. So that paper is not, I don't think it's consistent to do that. So this twist operator, so that doesn't respect conformal invariance, right? Right. So Cardi condition is a condition that if you view it in the open string frame, you need to have discrete spectra. So that's the Cardi condition. So the only boundary conditions allowed, at least in rational CFT, is the Cardi states.
They just have a sum over. They just have a Hilbert space, which is a direct sum over.
Oh no, that's fine.
Yeah, and they show that you get exactly the usual formula.
No.
Yeah.
What do you mean?
That's the main result is that you get.
No. The usual formula. The usual formula is equivalent to assigning blue circle a vacuum, which is very different from some of Cardi states.
No, it's enough to just take a sum of Cardi.
No. I'm pretty sure they're not considering all the Renyi replica numbers to do that.
Okay, perhaps I thought they had shown that it was you get the twist operator formula, but maybe
no. Well, if they claim that, they're probably wrong, or they're not looking at all the spectrum in Renyi reduced density matrix. So is it actually useful in computing the entanglement entropy? Yes, the partition function on a cylinder can be computed in the closed channel, right? In terms of the cylinder, and in a modular conjugated frame in this torus prescription. So because traced right away to the n is a partition function on the cylinder with circumference 2 pi n and length 2 log L over epsilon, you can just view this direction as time and view this direction as space and compute it like so. So it's you sandwich your boundary states using exponential of minus L over n. All is like 2 log L over epsilon of your S1 Hamiltonian. Or if you want to view it as a torus, you use the right-hand side, right equation. Okay. So how do you compute it? So because the length of the cylinder is very long, you can insert the complete set and approximate everything to a vacuum, right? So trace right away to the n. If you insert, for example, complete sets in 2 red circles, you will get B1, 0, 0, B2, which are like vacuum. Boundary entropy and exponential L over n times C over 12 because one second. Because the vacuum energy of a CFT on S1 is minus C over 12. Yes.
maybe you said this already, but B1 and B2 are boundary states of which theory?
Oh, so B1 is the boundary state living on the left side. B1 is the...
No, but like, do you have to do something extra because of the replicas, or it's just like standard boundary states?
It's a standard one, because boundary states are translational invariant, you know.
Oh, okay.
But there are important corrections, right? So that's the leading order corrections, but there are corrections of order exponential minus L over n times the gap of the Hamiltonian, because, you know, there are a bunch of states when you insert the complete set. And it's simply not modular invariant in order if you switch all of them at once. So after all, however, because L is very long or epsilon is very small, at leading order, the Rényi entropy is like C over 6 times log. Sorry, I'm forgetting probably n times n plus 1 over n, but at least this formula for the phenomenon entropy is like C over 6 times log L over epsilon plus the boundary entropy if there is a boundary, and corrections of exponential minus L over n times the gap. So this controls how much your open string approximation is correct, right? Open string picture is correct. And the expansion is valid when n is much smaller than log L over epsilon, because you need your cylinder to be long. So what was wrong? I mean, so why did you see inconsistency for the twist operator spectrum? Twist operator prescription is that I was taking n to be much larger than log L over epsilon. And it's allowed, you're allowed to do that because epsilon is just UV cutoff, and n is internal number you can give when you compute the Rényi entropy. You can, you know, increase n as much as you like and compute it. Okay? Yes.
Is B1 and B2?
It's a choice. You can choose anything you like, which is consistent.
Okay.
Like you can, for example, in spin systems, you can choose a free boundary condition or Neumann, Dirichlet, anything you like.
Okay. And but you're not summing over all the boundary states, right?
I don't want to do that.
You don't want to do that, yeah. Because, you know, boundary states is overcomplete, and
actually,
it's fine. Yeah, for your case, you are just taking only one single boundary state.
Yes.
Two also. In your...
I'm only taking 2 boundary states, one for left, one for right, and I'm fixing them.
Okay.
Just to say about my earlier question, I think this is all consistent with Hung and Wong. I think the basic point is that you can choose a sum over boundary states so that you get rid of the second term, but they also have exactly the order of distinct corrections which will play a role for you. Yeah.
Very nice, very nice, very nice, very nice. I see, very nice, I see. So you're talking about this one. I understand. Very nice. There is a quicker way to do it, which is to like simply make it a torus, which is, if you like it or not. Right.
Sorry, your remark is that they sum over the boundary states.
Sum over the boundary states, which is related to the vacuum Ishibashi state, which does it.
But my question is, you know, boundary states, they are overcomplete, right? They don't span. I mean, you know, they're overcomplete. All the boundary states, you know, the number of boundary states is much more than the, you know, Hilbert space dimension.
Yeah, I don't know.
Yeah, let's talk about it later. But I'm confused about it too, because if you only have vacuum Ishibashi state, I'm not sure if the open string spectrum is discrete or not.
Yeah, I think for them it is, but again, this is up to these order corrections. Like,
but I understand. Yeah. So with that reservations, I agree. Okay, very nice. So any other questions? Yes.
Which is larger, L delta gap or log L over epsilon?
Oh, I see, important. No, I was assuming delta gap to be order 1 because I wasn't taking any large C or anything.
I see, thank you.
It's just the second, you know, the dimension of the second lowest operator, I mean, after vacuum. Right, so the summary is that the bare entanglement spectrum of QFT is continuous, obviously, and only certain regularizations are compatible with probabilistic interpretations. And the regularized entanglement spectrum depends crucially on regularization. If you think about all Rényi all the eigenvalues of the reduced density matrix. And we cannot use our usual intuition about entanglement entropy in the large replica number regions. Right, any questions?
A question. So can you go back one slide?
Yes.
So if you take n to be very large, but still smaller than log over epsilon, but still like something like a log 1 over epsilon or something,
yes.
then this exponent of exponential minus L over n delta gap could be order 1, and I'm not sure whether they are really suppressed or not. So do you need an additional condition to neglect those like subleading terms, or is there any reason that you can neglect those?
I'm just saying that the delta gap is order 1, and I just want exponential minus L over n to be small. So this is equivalent to L over epsilon to, probably like, minus 1 over n, right? Because L is log L over epsilon. Okay. It's like this, and I want this to be very small.
Okay, I see. Thank you.
Very nice. So yeah, I've come halfway, and I'm on a good pace. I will continue to mathematics. Right. To be honest, I don't quite understand very much mathematics, but we still need to impose DV cutoff to define entanglement entropy, even in mathematics. They're not magicians. But they're usually phrased in terms of operator algebras and quantum states, and that makes it confusing, I guess. And I will explain how mathematicians define entanglement entropy, and then explain how we should understand it in terms of physics. So let's do a very quick recap of phenomenal algebras. So in the following, my spacetime is always compact, and I want my Hamiltonian to have discrete spectrum. And we're only interested in hyperfinite algebras, which I'm saying without understanding it, but I hear that it's the same as taking the limit of matrix algebras and the result of them. And they're known to be classified, I haven't followed the proof, but into type 1, 2, and 3. And the split property concerns the relation between type 1 and 3, so I'm not going to talk about type 2 today. So what's a type 1 algebra? This is something I can understand. Type 1 algebras are just matrix algebras, okay? So one example is the algebra of all bounded operators of QFT on a compact space. So I call it B of H. B of H means all the collection of bounded operators on Hilbert space H. Yes?
Definition of bounded operator?
You have the trace. So you have some trace and you compute the trace of it, it's finite. I think. Like exponential minus beta H. And
it's approximately defined as the magnitude of the largest eigenstate. And actually in quantum system, that doesn't happen.
Oh, I see.
Yeah, in quantum system, many of the operators are actually unbounded. Yeah.
No, I agree with this. Yeah. But I only want to take the bounded ones.
Okay.
Because that's what mathematicians talk about. Right, so just span the Hilbert space H with the energy eigenstate, and just nice matrices will define traces or bounded operators acting on them. Okay. So the density matrix rho is a member of B of H, and we can define the entropy properly, like trace of rho to the n, blah, blah, blah. You can do that. So one more non-trivial example is algebra of local operators of lattice systems, which is similar local operators, but they're just matrices, so they're just type 1. So for example, if you have like spin system of n qubits, you take finite sites, you don't take any thermodynamic limit or anything, you can define the entanglement entropy without regularization, right? So they're the example of type 1 algebras. So type 3 algebras, I think I have less, but let me explain. So let us resort to an n-spin system and later take n to infinity, because it seems like you can in general construct hyperfinite algebras using it. So imagine a spin system with n qubits. They're all written in Witten's review, so if you know, you know. R sub-region has n over 2 qubits. So I keep dropping this. nice. So imagine a spin system with n qubits. You take half spins out, and I name it my subsystem. So because I want to take n to be infinity, it's thermodynamically big, right? And each qubit is entangled with the counterpart. I wrote it by like pink arrows with temperature beta. And obviously, when temperature is like not zero, the entanglement entropy is infinite because n goes to infinity. So the physics trace of local operators acting on right spaces, right spins, is obviously infinite because it's it's like tensor product of infinite number of spins, so it's infinite. So you cannot either use mathematician's trick of redefining the traces like in type 2, because you can think of a candidate mathematics trace which is defined by you pick some member of the Hilbert space and then take the expectation value of operator and call it the trace for some reason. I don't know why they do that, but they do that. But mathematicians can only think about Hilbert spaces only containing finite excitations over my reference vacuum state, which is TFT temperature beta. I don't know. Again, I don't know why they want to limit themselves to do that, but they do that. And then what they are doing is simply, so for example, if you take psi to be TFT at temperature beta, its expectation value of O sandwiched by TFT, so it's simply the thermal trace, right, as you take n to infinity. And it's finite, usually finite. Usually finite. So you would be able to define some finite value using this construction, but it doesn't satisfy the cyclicity of the trace, right? Because if O is like the product of operators O1 and O2, because of the insertion of exponential minus beta h, it wouldn't be cyclic. So again, they limit themselves to considering some linear functional, which is like cyclic, and they don't like it. They somehow don't like it as a definition of the trace. All right, any questions? All right. Right, so one can vary beta for each qubit to construct type 3-1 algebra, which people say is relevant to like quantum field theory, because a type 3-1 algebra is characterized by continuous spectrum for the modular Hamiltonian minus infinity to infinity. And we obviously have that in QFT, right? So for example, if you take the Rindler wedge left and right, if you separate the space into left and right, consider the modular Hamiltonian, I mean, both sides. It's like, integral of x times t0, 0x. So it is continuous spectrum from minus infinity to infinity, and you happily associate it to type 3-1 algebra. Okay? Right. I guess you've listened to like reviews in week 1 and 2. Right, so the split property and the entanglement entropy. So is there, because it's type 3-1, is there no way to define entanglement entropy? No, it's not like this. The split property is known to hold, so you use the split property, and the split property is known to hold in all non-pathological CFTs, like with discrete spectrum, finite species, meaning that if you take some finite region of space and compute the partition function, it's not going to be infinite as you increase the temperature. So there is no like Hagedorn transformation. Now, the split property says the following. You take the subregion A and slightly larger subregion B, okay? Like it's my A, it's my B. And there exists, for normal CFTs, there always exists a type 1 algebra M, which is a matrix algebra, which is included in B, but includes A, right? So this is my type 3 algebra A, this is my type 3 algebra B, but there's an interpolating type 1 algebra M for like no ordinary CFTs. It's obviously not okay.
This is related to one of your other works, but is the split properties expected to hold in chiral QFTs?
Oh, yeah, very nice. It works for chiral CFTs. It works for chiral CFTs. You can prove it just by using differomorphism invariance. There is a paper by mathematicians proving that. But you still need full differomorphism invariance and modular invariance to prove that. So for example, right. I was going to say that. So by finite species and normal CFTs, I mean that, so mathematicians somehow think about CFTs where they have like, where their charge takes value in R or Q instead of Z, And they don't have this property.
Could you explain the subtlety a little bit? This is related to this Simeon-Hillerman kind of.
Yeah,
concern
and
that,
me, I guess.
you know, chiral CFTs
Yes,
is one
yes.
factor.
So I will get to this. I will get to this. So my secret motivation is because I thought that there wouldn't be entanglement entropy for gravitational anomalous theory. I wanted to understand what they do, what they mean by entanglement entropy in chiral CFTs. I will get to this. Very nice. So now recap is that there exists a type of algebra M such that, you know, interpolating A and B. And in other words, there is a unitary map. You know, I will call it the split map U such that H goes to HM tensor HM dot R, and HM is the collection of bounded operators in HM. M, the phenomenal algebra M is a bounded collection of bounded operators of HM, by which I should write M is B of HM. This is what I meant to write. It's a little complicated, but UA U inverse is A tensor 1, and UB prime inverse, U inverse is 1 tensor B prime. Pictorially, any operator living here goes to the same place on the left space. Any operator living here goes to the same place on the right Hilbert space. Okay. And it's very important, there are infinitely many possible M, or equivalently U, you know, it's important. All right, any questions for the formalism? Nice. Right, so I'm going to talk about this split map U, and we can then, if there is such a thing, we can define the regularized reduced tensor matrix by having like U row U inverse, and then taking the partial trace, and you define it to be your reduced density matrix. Very nice. Finally, there is also a canonical choice in M that mathematicians like, which is to do this, which is complicated, but roughly, which means that you use the modular operator on the buffer region, by which I mean B cap A bar, so these regions, to map your operator to the right space. In particular, because the modular operator on a disjoint interval is non-local, what they do is to take these operators and then mix them together and distribute them like, in these regions consistently. Okay. So that's what they do. That's what they like. And if you define your entanglement entropy according to this split map U, you will call it the canonical entanglement entropy. Yes.
Sorry, is the J the relative modular conjugation of the absolute? Is it like delta? Is it J omega line omega tensor omega? Or
I think J was J of omega.
just J omega?
I think.
Oh, okay.
Oh, but the right side is like, is a canonical type 1 factor.
Is J just equal to A prime?
1 second. No. J is on these regions. So
Should that be B intersection A bar over there?
come again?
So it's is it okay? You're saying it's the J of the buffer region, is all you're saying.
Right, J of the buffer region. So A will be mapped to here, but because A and B bar maps to the whole space, AA maps to like some like scattered points on the buffer region. Right. So now that we've reviewed the mathematics, let's connect the two. Right. So it's hard to compute anything in this mathematics definition. It's hard to compute the canonical entanglement entropy, which is only known to be finite instead of infinite. But there's a physics way, the path integral. So use this path integral on a strip. I call it I0. So this strip, what does this strip do? So the lower line represents the state on the total Hilbert space, and the upper one represents the Hilbert states which are factorized. And so I take A to be living inside the inner region, B to be outside region. And we can either give boundary conditions a purple region or identify them depending on if you want to like compute it as a boundary condition or the torus. Okay, if you remember it. So what you do is you have vacuum and you evolve it using this strip path integral, and you assign like branch cuts and then compute it. So after conformal transformations, they map to like either finite length cylinder or a torus. Very nice. Now, I0 is not a split map per se, right? Because we don't have, so this operator doesn't map operator in A to like unit, with like unit action, right? Because it's a Euclidean path integral. If you have an operator in A, like it spreads all over. Second, I0 is not unitary because it's a Euclidean path integral. So you can remedy easily the first by considering the Euclidean time evolution with a deformed Hamiltonian, which Das talked about. So it's similar to the sine squared deformation, but you have zero. So you like envelope your Hamiltonian density with g of x, which takes only values inside this buffer region, like this, right? So if you have an operator here, it's not going to be evolved according to this Euclidean path integral, Euclidean time evolution. And this is the same as taking a different quantization surface in 2D, CFT, right? So it's a sum of like Virasoro operator weight by the Fourier transform of G. Okay. Right, so I call it I, and I is not still unitary, right? Well, this is okay. You have a map U, which is unitary, would be unitary, if you define it U to be I times I dagger I to minus 1/2. So this is going to be unitary because if you have U dagger and U dagger U, and it's going to be 1. But, however, you need to have an inverse for I and I dagger. I'm not going to show you the proof of it because it's a little complicated, but you prove it first in a dense subspace of finite energy states and extend it to the whole Hilbert space. And on this dense subspace of finite energy states, and this is simply a consequence of Ricci-Leiter theorem. So my punchline is that I has an inverse, I dagger has an inverse. You can freely define the operator U, and this is unitary. And this works as a split map. Okay. Nice. So you can do whatever you like to the boundary, but different ways lead to different type 1 algebra. So for example, if you impose the boundary condition, unitary boundary conditions, you will get M as the B of HBCFT. But all the algebra on this BCFT. If you impose the periodic boundary condition, we get S1 algebra on S1. That's it. Right. So I will get to this canonical type 1 factor, which Suvrat asked, because it seems like you can define. In particular, it's very important that you can't do the first construction if your theory was gravitationally anomalous or chiral CFTs, because you don't have any boundary conditions for chiral theories. But it's okay. You can define a canonical entanglement entropy because canonical type 1 factor falls under the periodic boundary condition. So again, what you did is to take these buffer regions and mix them non-locally and then distribute it on the purple regions on the left-hand side, right? Because the modular operator on this joint union is non-local and inevitably mixes the two buffer regions and distribute them. So it's the same as having an S1. You do a path integral on a Panzer-like geometry. So that's what they're doing. So they inevitably introduce non-locality in the entanglement spectrum, entanglement Hamiltonian. And we need to make sure what we mean by entanglement entropy then when we talk about your Takayanagi formula. If we say we are using mathematicians' entanglement entropy and phenomenal algebra to define to do that, I don't know what they're doing, because you inevitably need to like identify the two entanglement points, which is a non-local procedure, and I don't think you want to change the system as much as that. Right. So finally, any questions?
I didn't understand why the canonical type 1 factor has to do with periodic boundary conditions. You said there's some Panch diagram. Can you draw the Panch diagram?
Mm-hmm. So no, what I meant is the following. So maybe I should write here because, yeah. So you do this path integral, basically, modulo some like modifications. So if you were to use, so what they're doing is to, I don't know, take the buffer region and use the modular Hamiltonian to map them. So even if they're separate, they were like separated in space, they mix these operators together. So that inevitably brings you a periodic boundary condition, because if you evolve your operator using modular Hamiltonian, if you come here because of this procedure, you will get back to it.
Are you making a heuristic statement or a precise statement?
It's a rough statement, but I think it can be made precise in a sense.
Okay. So heuristically, you're just saying that it's
right.
Physics. Okay.
Very nice. Thank you. So finally, applications to I couldn't complete the slide, so I need to do it in Blackboard. So one application to ADS-CFT is that if you take holographic theories and take large N, even though you thought it had type split property, you lose it, right? It's not very deep. So in order to compute the entanglement spectrum, you will, if you impose a periodic boundary condition, you will have the torus partition function. On the Hamiltonian S1 is your entanglement Hamiltonian. But this entanglement Hamiltonian has discrete spectrum around the vacuum, but it starts being, so if it's 0, it's like C/12 or something. So at order C, your entanglement Hamiltonian starts being continuous. Okay, and you start to see it at the Renyi index to be 1 up to like log L over epsilon over 1 over n is much greater than 1. So this usual region where you compute the von Neumann entanglement entropy is related to the continuous spectrum in your modular Hamiltonian. And you can maybe call it the type 1 to type 3 transition according to the replica number. So you're looking at the n goes to infinity region because you're only probing the discrete spectrum when you take the replica number to be large, because you're only looking at the low energy region of your modular Hamiltonian. Okay? Right, so outlook. So I want to say not all regularizations are allowed in computing entanglement entropy, and we're usually using the wrong one, but get away with it as we only look at von Neumann entropy. If you go to large replica limit, you will see inconsistencies. This will be also important in studying the replica wormholes, because the computation of Malsin and others will break down a large replica number. So just because we know that at replica number n is equal to 1 plus epsilon, it works. The semi-classical computation can recover quantum information doesn't mean that there are no UV consistency of quantum gravity hiding a large n region. And also, I want to point out that maybe it's not clear what we mean by Takayanagi or Shidon formula in the precise sense, if you take a large replica number, because there will be phase transitions in the Hawking-Page sense from small n to large n, and then your saddle point the form of your saddle point in ADS space will change. So I think this is not only quantum version problem of the quantum version of the Takayanagi, but the semi-classical version of it. Thank you very much. Any questions?
And n goes to infinite to only probes a low energy. Could you explain that?
Sorry, yes, it's my fault because I didn't explain it properly. So I was going to say that trace, maybe it's hard to see. No, it's not very deep. Trace of rho a to the n can be computed as a partition function on a cylinder with circumference 2 pi n, and this is log L over epsilon. Okay, so N is so if you think about 2 pi N to be the temperature, the generator in this direction is the Hamiltonian. It's simply trace minus 2 pi N, your modular Hamiltonian. So if you're at large N, you're at the low temperature region.
So you mean the low energy in the sense of modular energy?
Modular temperature, yes.
I see, thank you.